So today we'll be looking at alkenes. So alkenes are obtained by hydrocarbon cracking, and I've discussed the process of cracking in a previous video on alkanes. Alkenes are part of the aliphatic family of hydrocarbons, and aliphatic compounds are any compound that do not have a benzene ring. So alkenes, alkynes, and alkanes are all part of the aliphatic family. The general formula of alkenes is CnH2n. They are often referred to as unsaturated hydrocarbons, and this is because they have a CC double bond, so the carbon and the carbon next to it have a double bond, so which allows alkenes to absorb more hydrogen atoms if this double bond is broken. So what exactly is a double bond? So first of all, let's consider sigma bonds, and these are a type of a covalent bond whereby two atomic orbitals have a head-on overlap, like pictured here. So in this case, the two carbons have an sp2-sp2 overlap. And the two electrons are shared between the two carbon nuclei, and the electron density is concentrated in the middle of the sigma bond. So sigma bonds are also known as single bonds. However, a double bond contains one sigma bond and one pi bond. So let's look at what a pi bond is. So pi bonds happen when p orbitals overlap, and this happens sideways, above, like here, and below the plane of the molecule. So again, we can see the sigma bond here and the two p orbitals overlapping at the top, and this is known as the pi bond. So in order to have a double bond, you would need one sigma bond and one pi bond. And the importance of this is that when you have a double bond, there is no rotation. So no rotation can occur about the double bond. In order for rotation to happen, you would first need to break the pi bonds, and breaking a pi bond requires a lot of energy. Okay, so let's consider how to name alkenes. So as with alkanes, we first look at the longest carbon chain that contains the carbon-carbon double bond. So I've put the prefixes here again. So from the previous video, we remember that if you have one carbon, it's methane, 2 is ethane, 3 is propane. In this case, it would be the same, instead that the ending would be -ene because it's an alkene. So let's consider this example here. So let's first count how many carbon atoms there are in this chain. So we have 1, 2, 3, 4, 5. Therefore it's pent, and because there is a double bond here, it is a pentene. So that's the first stage of naming an alkene. The second stage is to give the lowest possible number to the carbon-carbon double bond. So for example here, we know that we can see that the double bond is here, and it's on the first carbon. Therefore it's pent1-ene. It would be wrong to start counting from this end. So if we were to do it the wrong way, we would say 1, 2, 3, 4, but to name it pent4-ene would be wrong because it's not the lowest possible number. We can also look at this one here. So first of all, let's consider the long chain is 1, 2, 3, 4, 5, 6. 6 is hex because we have a double bond, it's hexene, and we also have to specify where the double bond is. So if we start from counting from this side, it's 1, 2, 3. And from this side, 1, 2, 3. Therefore, it's hex3-ene because it's equal from both sides. Okay, so let's look at naming alkenes with branches and functional groups. So we've just do for a quick recap. So far we've talked about counting the longest chain of carbons, then giving the double bond a number, and the ending of alkenes is -ene. So if there are any other substituents, we would use the prefix. So for example, if we have a halogen, for example chlorine, then we would use the prefix of chloro. Or if you have any alkyl groups like methyl or ethyl, again this would be the name. And again, we would then need to give the substituent the lowest possible number for the associated carbon atom in the main chain, but these lowest substituent numbers are determined by the number assigned to the ene group, which is the double bond. So they can end up seeing a bit high because of the high ranking of the ene functional group. So let's consider this molecule here. First of all, we will count the longest carbon chain. So we have 1, 2, 3, 4, 5, 6. Therefore, it's hex. Because we have a double bond, it's hexene. So we need to assign the lowest number of the double bond. So it's obvious that it would be hex 1ene, because if we started from this end, it would be 1, 2, 3, 4, 5, which is definitely not the lowest number. And then we also have this methyl group here. So as mentioned before, because we have already started numbering from this end of the molecule with the double bond, therefore this can't really be 1 as well. So this will be 1, 2, 3, 4, 5. 5 methyl hex 1ene. We can also consider this molecule here. Again, first we count the longest carbon chain, 1, 2, 3, 4. Therefore it's but. Because we have a double bond, it's an ene. To assign the lowest possible number, we have to start from this end, therefore it's but 1ene. And we also have a chlorine here, so we need to specify where the chlorine is. So since the double bond is on 1, so we start counting from here, it's 1, 2, 3, therefore it's 3 chlorobut1ene. And if we have a molecule that has a ring of carbon atoms, including the double bond, we simply put the prefix of cyclo, as in this example, we count the number of carbons in the ring, so we go 1, 2, 3, 4, 5, 6, so it's a hexene because there's a double bond, and because they are arranged in a ring structure, we put cyclohexene in the beginning. We do not need to assign a number of the double bond because it can be anywhere and it still would be 1, because we would start counting from that carbon. Let's now consider isomerism. Alkenes that have 4 or more carbon atoms show structural isomerism. This means that they have the same molecular formula, but 2 or more different structural formulae that you can draw to represent this. Stereoisomers are when atoms in the isomers are joined up in the same order but have different arrangements in space. So for example, with C4H8, it's not too difficult to come up with 3 structural isomers that are drawn out here. We have but1ene, but2ene, and 2-methylpropene. However, there is another isomer, and it applies to but2ene. And this is known as geometric or cis and trans isomerism. And this happens because the carbon-carbon double bond doesn't allow any rotation about it. Therefore, it is possible to have the methyl groups on either end of the molecule to be locked in a particular position. Like in this example, we have the 2 methyl groups are on the same side of the double bond, and here the 2 methyl groups are across the double bond. So it's quite important to specify which isomer we are dealing with, and then in this case we use the prefix cis, which signifies that the groups are on the same side. So here we can see that the 2 methyl groups are on the same side, therefore it's cis-but2ene. And when the groups are on opposite sides, we use trans. And you can remember trans by thinking of a transatlantic flight. Okay, so let's look at naming cis and trans isomers. So we can see here that because no rotation can happen about the double bond, these green circles are locked in that position. And we can use the trans and cis naming system when we have let's say, chlorine on this side and also another chlorine on this side, then it's quite easy to see which one is repeating. And in this case, we've also got 2 chlorines and hydrogen, so it's cis-1,2-dichloroethene. However, if we look at this drawing here, this is the same molecule. As to get the other one, we simply have to turn the whole molecule over. So in this case, there is no geometric isomerism. So in order to have geometric isomerism, we need to have 2 different groups on the left carbon and 2 different groups attached to the right carbon, to the carbon that's participating in the double bond, like here. So we need to have, rather than having 2 pink ones on the side, on one side, attached to one carbon, we need to have 2 different, so in this case, pink and blue. So we've considered cis and trans, but there is another system which is called EZ isomerism, or EZ naming, and this is used for more complicated compounds. So for example, if we look at these 2 molecules here, we can see that we have chlorine and hydrogen, and we have bromine and fluorine. Well, how would you be able to name that? Because they're not the same, therefore we can't say, well, chlorine and fluorine. Therefore we use something called EZ, and this naming works by giving each attached end a priority. So if we look at this example here, bromine has higher priority over fluorine, and on this side the chlorine has a higher priority over hydrogen. So this, because both of the higher priority groups are on one side, this would have a Z prefix. And if we look on this, if we look here, we see that bromine has a higher priority over fluorine again, and in this case chlorine again has a higher priority over hydrogen. But now the 2 high priority groups are across from each other, therefore they are E isomers. And E and Z comes from the German language, where Z stands for zusammen, which is together, meaning that they're on the same side, and E is for entgegen, which is across from each other. Okay, so how do we determine priority? And this is quite simple. We simply have the atom with the highest atomic number has a higher priority. So in this case, we have hydrogen and chlorine. And hydrogen has the atomic number of 1, and chlorine is much bigger. Therefore, chlorine on this side has higher priority. And the same applies to this side, equally here. Therefore, because both the chlorines, which have the higher priority, are across from each other, they are E isomers. And here, because both of the high priority groups are on the same side, they are Z. So what happens if we have let's say, not just chlorine or hydrogen or oxygen attached? What is if we have a group of atoms? Well, we simply have to look at the atoms that are directly attached to the carbon. So in this case, we've got a hydrogen, which is the atomic number of 1, and we have carbon, which is directly attached to this carbon. And carbon is much bigger, therefore it has higher priority. And the same here, therefore it is E-butene, because both of the high priority groups are across from each other. Let's consider a slightly more complicated molecule, shown in the right hand corner here. I've drawn out the molecule here just to explain how we would give priority to more complicated structures. And so let's first consider the left hand side, which is on the left carbon. So first we need to ask ourselves what is attached directly to the carbon which is in the double bond. So in this case we have, in red I've highlighted that we've got 1 carbon here, 1 carbon here. But they both have the same atomic number, so they're equal in priority. So then we need to see what is attached to these 2 carbons. So At the top we have 3 H's attached, so we write out HHH, and in the bottom the atoms that are directly attached to this carbon are 2 hydrogens and another carbon. So we write out CHH. And the reason why I wrote C first is because it has a higher atomic number. So now we can simply compare what is connected to the top carbon and what is connected to the bottom carbon. We can see that we've got a hydrogen and a carbon here, and because carbon has a higher atomic number, it has higher priority, so therefore the whole of this molecule has also higher priority over the methyl group at the top. So let's look on the right hand side at these groups here. So again, we first look what is directly attached to the carbon in the double bond, and again we have 2 C's, which are again equal in priority. So then we look further to see what is attached to these 2 carbons now. So at the top we have hydrogen, hydrogen and oxygen. So again we have to write it out as OHH because oxygen has a higher atomic number. We do the same for the bottom. So we have hydrogen and a double bonded oxygen. And we write this out as OOH. And the reason why, because we have 2 covalent bonds here, therefore oxygen is counted twice. Now we can again compare the top and the bottom. So the first we've got O, and they both have the same atomic number, so equal in priority. So then we go on to the next one. We've got a hydrogen and the oxygen, and we know that oxygen has a higher priority because it has a higher atomic number than hydrogen. Therefore the whole of the bottom group has higher priority over this group here. So now that we know that this group, so this bottom group is higher priority, and on this side this group has higher priority, we can now see that because they're both on the same side, this isomer would be called a Z isomer. Let's now look at reactions of alkenes. So first of all, let's discuss the reactivity of the carbon-carbon double bond. So to see the difference between a double and a single bond, we can use average bond enthalpies, and bond enthalpies are the measurement of the strength of a covalent bond. So we can see that in order to break a carbon-carbon single bond, you need 347 kilojoules per mole, whereas to break a double bond, you need nearly double as much energy. So double bonds are stronger than single bonds. Another important thing to know is that a pi bond is weaker than a single bond. So when alkenes react, the pi bond breaks, but the sigma bond remains intact. So in the next, on the next few slides, we will cover the key reactions. First of all, we'll look at addition of hydrogen. We will also look at the addition of halogens to produce halogenoalkanes. We'll also look at the mechanism. Also addition of hydrogen halides, again also to produce halogenoalkanes, and also the final point would be to look at oxidation of the double bond by potassium manganate to produce a diol. So let's now first look at the addition of hydrogen. This is also known as hydrogenation, and this is an addition reaction where the pi bond breaks and a molecule is added. And usually we would go from an unsaturated alkene with a double bond going to a saturated product like here. So in this case here we've got hydrogen gas, and hydrogen is a diatomic molecule, so there's 2 hydrogens here, and the alkene is also in a gaseous state, and they are passed over a catalyst, usually nickel, at about 150 degrees centigrade. We use nickel because it has a large surface area, therefore it has high catalytic activity, so it helps to increase the rate of this reaction. And the reason why we use hydrogenation, the main use of this process is to make liquid oils into semi-solid or solid fats, so to go from liquid to solid fats. But just be aware of the health concerns that are associated with the hydrogenation of unsaturated dietary fats to produce saturated fats and trans fats. So that's hydrogenation. Let's now look at halogenation of alkenes. And this involves an alkene reacting either with fluorine, chlorine, bromine, or iodine. Also, just bear in mind that all halogens again are diatomic. So they have, it'll be F2, CH2, Br2, and I2. Therefore, the product is disubstituted. So let's first look at ethene and fluorine. It's a very explosive reaction, and the products are hydrogen fluoride and carbon. So it's not a very useful reaction. Let's also look at ethene and chlorine. So as I mentioned before, the product will be a disubstituted halogenoalkane. Disubstituted meaning that the double bond in the ethene will break the pi bonds. The pi bonds will break, and because there are two chlorines here, they will attach there. And the name of this product is 1,2-dichloroethane. So again, we're going from a alkene to an alkane. Here we have an example of when bromine reacts with an alkene, in this case ethene. Again, the same thing happens because there are two BRs here. The double bond will break and the two BRs will attach here to produce 1,2-dibromoethane. And the reaction between ethene or any alkene with bromine usually produces a color change, where it goes from orange here, goes to colorless. And this happens because the bromine is reacting and breaking apart the double bond and attaches itself to the new alkane. And this is a test we use for looking if there is a double bond present. So let's now look at the addition mechanism, specifically with bromine. So here we can see bromine at the bottom here, and this is our alkene. So bromine is a non-polar molecule, but when bromine approaches the alkene, the electrons in the pi bonds repel the electrons in the Br-Br bond, and this induces a dipole in the Br2 molecule, meaning that one end will be delta plus and one will be delta minus. So now the Br molecule is slightly polar. The electron pair in the pi bond is attracted to the slightly positive bromine atom, causing the double bond to break, and we represent this with this curly arrow, and this represents the movement of the electrons. A new bond forms between one of the carbon atoms and the bromine atom, which is shown here. So this is the delta positive end of the bromine has attached itself here, and we can see there's no more double bond here. Just to be aware, the Br bond breaks by heterolytic fission, with the electron pair going to the bromine. And I put just some key definitions here. So heterolytic fission refers to the breaking of a covalent bond with both of the bonded electrons going to one of the atoms. So they either form a cation or an anion. So in this case we have bromine Br minus forming. So the bromide ion here and their carbocations are formed. The carbocation or carbocation, depending which way you want to pronounce it, is an organic ion in which a carbon atom has a positive charge, represented with the plus sign here. So the positively charged carbocation is unstable and therefore quickly reacts with the bromide ion to form the organic product shown here. And again, we show with this blue arrow, we're showing the movement of electrons to form the new bond. And in this arrow here, is showing that the bond is splitting, and the electrons that were shared here are going to the bromine to form a bromide ion. In this mechanism, the bonds are broken by heterolytic fission, and ions are formed as the intermediates. So this step here, where the carbocation is formed, is called the intermediate step before we get the final product, which is the di-substituted alkane with the two bromines attached there. Just a few definitions again. So electrophilic addition, this is an example of electrophilic addition, is an addition reaction where an electrophile is something that is attracted to a negative region. So phile, the end of the word, means it's loving, and electro, so it's electron loving, is attached to an electron-rich center or atom where it accepts a pair of electrons to form a new covalent bond. And a mechanism, which we described here, is a sequence of steps showing the path taken by the electrons in the reaction. So these curly arrows that we used show the movement of the electrons. So in this case, this arrow represents double bond breaking. This arrow represents that an electron that was previously shared between the two bromines is going to this bromine, forming a Br minus. And then here we can see a new bond forming between the carbocation and the bromide ion. So let's just quickly look at bromine water, which is used to test for alkenes. As I mentioned previously, there will be a color change, so it will go from orange to colorless. But there's something to be aware of. The reaction that I mentioned before was just an alkene reacting with pure bromine. However, when we use bromine water, water is also present. So in this case, the major product would not be 1,2-dibromoethane, but we also have to be aware that water will also be reacting here, which will then produce another molecule, the major product of this reaction would be 2-bromoethanol, which is an alcohol, and hydrogen bromide. Of course, there'll still be 1,2-dibromoethane, but we just need to be aware that because we're adding water, there is like another reaction that is also happening. So there'll be a mixture of 2-bromoethanol here and 1,2-dibromoethane.